In this video, we're going to take a look at resonance structures and a concept called delocalization. So let's start out with an example, and we're going to draw the Lewis structure of ozone. So remember, ozone has 6 valence, or each oxygen has 6 valence electrons, and we've got 3 of them. So we should have 18 electrons total in our Lewis structure. So if we were to draw this, we're going to do 3 oxygens, and then we're going to fill our outside atoms, up to the octet rule. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18. Now, this Lewis structure here is not quite complete because our central atom doesn't have a filled octet. So we are going to take one of these pairs of electrons here, and for some reason my eraser is not working, so I'm just going to draw it below instead, and we're going to share it as a double bond. So we're going to end up with a structure like this, where one oxygen is going to have a single bond to one oxygen, and then one oxygen is going to have a double bond to one oxygen. So this is our typical Lewis structure that we would draw. And the way it's drawn does suggest we've got a double bond and we've got a single bond. However, in reality, ozone is a hybrid of these structures. So we could draw another resonance structure here where we have a single bond on the other side and we have our double bond on the other side. So we've got our 2 resonance structures, but really, ozone's a hybrid between these 2 resonance structures. So let's take a look at some data to see why this is the case. So if we take a look at data, and we take a look at the bond length and strength data that's shown, we have single OO bonds have a bond length of 148, whereas a double oxygen bond has a length of 121. And if we look at the energy, the bond enthalpy, we'll define what enthalpy is in a separate video, but this is essentially the energy it takes to break that bond. For the single bond, quite low, and for the double bond, it's quite a bit higher. And so if we look at the data for the oxygen bonds in ozone, they're actually found to have a length of 127, which is between the 2 here, and both bonds are found to be equal in length. So the bond length and strength data that's shown shows that the 2 bonds in ozone are identical to each other, and there we would say they are intermediate between a single and a double bond in terms of strength and length. And so if we were talking about these bonds, we would say that the bond order is 1.5. So it's like we have 1.5 bonds between them. Like we don't actually have 1.5 bonds, but it's like we have 1.5 bonds instead of the single bond being a bond order of 1 and the double bond being a bond order of 2. So what this means is that the electrons in the double bond or the pi bond is being shared equally between all of these different multiple bonding positions. So you can picture we've got a p orbital on this one, a p orbital on the middle oxygen, and a p orbital on the other oxygen. And these are 3 sort of p orbitals that the electrons can be shared equally. Let's get a green here, between these pi orbitals. And so that creates something that's known as delocalization. So anytime that we have a resonance structure or resonance structures for a molecule, we have delocalization. And we can represent a resonance hybrid in a slightly different way using a drawing. So it's important to note resonance hybrids are not Lewis formulas because they don't show all the valence electrons. So what we're going to do here to show the one for ozone is we're just going to draw the 3 oxygens. We're going to keep the angle in there, And we're going to show our single bonds as solid lines. And then we're going to show our delocalized electrons with dotted lines to represent that those are all the positions that we can have those delocalized electrons in, meaning that they're not fixed on one single atom. So we're going to use dashed lines to show the delocalization here. So each oxygen bond has a solid line, which represents our sigma bonds, and then the dotted line to represent our delocalized electrons. Now, if this was an an ion, we would still need to draw in our square brackets and our charges as well. So just something else to keep in mind. But this would be our resonance hybrid structure, not showing all of our valence electrons for ozone. So that's it for this video. We'll see you in the next one.